in SPI, originally, we had these devices out here, and LCD, these pins die so quickly. And we had, we said there's SDO and SDI, and SDI, SDO, and the SCK, this is the microcontroller. There's an alternative terminology that a lot of companies, I think, try to avoid because of maybe some negative connotations. When you're using SPI, there's one device that's in control of all the other devices. And in our case, it's the microcontroller. And the devices that are under control are these devices over here. And so the technology that they use, they called this the master, and these were the slave devices. And I think some companies, to try to be politically correct, don't like to use the term slave. And but you'll find chips out there where SDO for here is because the naming conventions that they use when they use master and slave were very clear. This line over here on a master device would be called master out, slave in, or MOSI, M-O-S-I. And then this one would be called master in, slave out, MISO. And you'll see parts that say that. And so over here, this would be, it would just hook up to the data in, and the data out would hook up to the MISO, master in, slave out. And I was thinking, on the way over here, if they don't like that, maybe what they should call would be the director and the actors. Right? So the director's in control, and the actors are the ones that are listening to the director. Maybe, and then you could call it DOAI. DOAI. Doesn't roll out. And of course, there was the chip select. And there's a chip select for this device, and then there'd be a different chip select. We looked at the bits when we transferred, but what we didn't look at is how the code sets that up. The SPI, you need SPI.h. And when you include SPI.h, it allows you to add some commands, and to set it up, you say SPI.begin. Similar to when you do serial, you say serial.begin. Here you do SPI.begin. And then there's this SPI.setClock divisor, and SPI clock divided by 64. And what this is, it kind of, when serial, when you set up the bit rate, bits per second, this sets up the clock rate, how fast the clock goes. Because I think I mentioned last time, right, the clock is coming from the master. So the clock is coming out of the microcontroller, so it sets the speed. So the clock divided by 64 says there's some internal peripheral clock, and whatever its full running speed is, it divides it by 64 to slow it way down, because some chips just can't communicate that fast. And I don't recall off the top of my head what that clock rate is. When you do the lab, one of the first things you do is hook up the oscilloscope, so it's easy to measure what the resultant clock speed is. The chip select is just a general purpose digital output. You need to pick a pin that's going to be your chip select and set it as an output. So in this lab, pin 7 is going to be the chip select, so pin 7 is set to an output. And then to actually transmit data, you set your chip select low, the digital write chip select low, and that makes the chip select pin go to logic low. And then SPI.transfer, and that transmits the data A3, and then digital write chip select high. We had the serial data out, and we had our serial clock. This example doesn't use input, it's just transmitting. So we have the serial clock, and we have our chip select. So we got those three signals coming out, and we're going to look at them versus time. So if this is time, the first thing that happens in this code is the chip select line goes low. So let's say it's at some high level, and it goes low, and it will stay low until our transmission is complete, and then go high. The next thing it says is transfer A3. So our data line is going to be in some unknown condition, and then it's going to transfer A3. So A3 in binary is 10100011. And so we don't know the previous state of this data, and then there's going to be a transition that results with the data going high, and we're going to have 1, 0, 1, 0, 0, 0, 1, 1, and then it will look like that. And it will probably, after this point, stay at the previous high condition. And the clock will, depending on the mode that's selected, will do something like that. It'll do a rising edge on the transition, and then a falling edge while the data is solid. And the last thing that happens is the chip select this high. And the first thing we do in this lab is hook up the oscilloscope to these three signals and look at this. Now, from the serial lab, where we looked at the signal that we're transmitting, you will recall, hopefully, I think everybody did it, that you need to trigger off the lowest frequency signal. Chip select, yes. Chip select is the lowest frequency signal. So you're going to need to trigger off the chip select. Now, there is a problem with our oscilloscopes. It's not a horrible problem, but we only have 2 channels. So there's 2 channels on the oscilloscope, but conveniently we have a third input that's called the trigger input. And so what we'll be able to do is graph these 2 signals on the graticule, but the trigger will have to go from the chip select, and you won't be able to see it. Now, what you can do, though, is you can get these signals up there, and maybe you have some syncing issues or whatever. They're on the screen, and you can see some transitions, but they're not quite synced up right. What you could do is you could take one of these signals off, put the chip select over here, make sure you have a good chip select, and then move it back, and then change your trigger up here from channel 2 to the external, EXT. So when it's on EXT, it uses that third output. All right.